P is not known. Okay, now we shall define what is Poisson distribution. So this is a limiting case of binomial distribution where we saw P equals to lambda by n, Q equals to 1 minus lambda by n. Here, as n tends to infinity, P tends to 0. That means when n is indefinitely large, P is going to be indefinitely very small. In that case, the probability function is given by Px equal to x equals to e to the power negative lambda, then lambda raised to the power x divided by x factorial, and the values of x can be 0, 1, 2, 3, dot dot dot. So this is also up to infinity. That means we are not sure that how long it's going to be along the line of infinity. Another speciality of this distribution is its mean is lambda and also the variance is lambda. That means mean and variance of this distribution is the same, and that sort of proof I'm going to discuss in another class. Now it's very important to understand under what condition the Poisson distribution is appropriate. So what should be the conditions for the Poisson distribution to be Poisson? Here the condition is like the random variable x should be discrete and that occurs in a unit interval of change. Here the change means per unit of time, per unit of distance, per unit of volume, per unit of mass, etc. That means there should be some specific equal spacing in the happening of the events. And most importantly here, this is another condition is that the occurrence of the events must be random and occur independently. So the experiment should be random and the occurrence of the outcome should be independent. Now another feature is this is n. N is the number of trials. It should be indefinitely large, as here n tends to infinity, and the constant probability, you can see here the constant probability of success P for each trial is indefinitely small. That means when n tends to infinity, you can see here in like this is the probability value that we have got. So when you apply very large value of n here, then P is going to be very small because this sort of thing is going to be divided by very large value. So this ratio will become smaller and smaller as n increases. Therefore, P tends to the indefinitely small value. So this is one of the condition for the Poisson distribution. So that is P tends to 0 and must be uniformly distributed over the interval under functioning. Interval under functioning means where the changes are going to take place. That's why we can say that should be uniformly distributed over the under the functioning interval. Now we shall discuss some example. I'll solve it here in order to see that how the Poisson distribution formula can be applied to the given problem area. So first of all, I'll try question number 1. So here we know that Px equal to x equals to this formula, and then we'll use the same formula to each of these problems. So here if I start Px equals to 0, then if I use the formula, then e to the power lambda value is, in this case you can see the lambda value is, this is the parametric values, this is the place for lambda, and hence the lambda value is 3.4. so this is the place of lambda, so we put this value lambda equals to 3.4. so here it is 3.4 and then times we have lambda again here, so it is 3.4 to the power x, means we are working with x equal to 0, so in place of x there is going to be 0 and whole thing divided by x factorial means 0 factorial. Now you know that any number like 3.4 power 0 is 1 and also 0 factorial is 1, therefore this sort of thing will be equal to 1, and then you are left with e to the power negative 3.4. Now take your calculator and try this calculation for e to the power negative 3.5. so here I'll press shift then ln, I'll start bracket because I'm dealing with negative sign, so this is important to use the bracket whenever you deal with the negative sign. So it is negative 3.4. So 3.4, and then I close the bracket. My answer is 0.0333732 and 6 and few more decimal values. And we don't need to write everything in the answer. So our answer up to 3 significant figure is 0.033, and here you can see these two values 37. So the neighborhood there is value more than 5, so this 3 will become 4. So this is up to 3 significant figure. Now we'll do question number 2 now. So in question number 2, you need to find px is greater than or equal to 1. So in that case, as you have here you can see px greater or equal to 1. That means what sort of value x is going to take here. So x is equals to 1, 2, 3, 4 and so on. We don't know how long it will go ahead. So it is not possible here to calculate this probability. Therefore, we use the complementary probability theory, where we can write px is less than 1. And that sort of work we have learned while dealing with probability distribution, and also we have applied widely in binomial distribution. So now it's almost clear now. So it is 1 minus p, and the number which is less than 1 is x equals to 0, and then 1 minus, we just keep into mind your this sort of formula, but you don't need to write all this sort of thing. So because we know that at x equal to 0 it's going to be e to the power negative lambda. So in place of lambda we have 3.4, and 1 minus, we already have this value now, so 0.0334, and then it's still in my calculator. I only need -1, so I write here -1. My calculator value is in negative sense, but because I applied in opposite way, but you can write your answer in positive sense, and it says that this value is 0.966626 with few more decimal. But we need the answer up to 3 significant figure, so we can round off this to 3 significant figure. That means this is 0.967 up to 3 significant figure. We have for me few more problems to do. So we have done up to 2. Now I'll try question number 3. So I'll just fold it. Now you can see in question number 3, you need to find px is less than 3. So in this case, you know that if this is px is less than 3, you can write px equals to 0 plus px equals to 1 plus px equals to 2. We don't write px equal to 3 because according to this inequality inside the bracket, it doesn't include 3. Therefore, we write up to 2. Now we apply the same formula here, e to the power negative lambda, and lambda value was 3.4, and then it is 0 means 3.4 to the power 0 over 0 factorial, and 0 factorial, then we work for this. So e to the power negative 3.4 times 3.4 to the power 1 and 1 factorial because x equals to 1, and here it is e to the power negative 3.4 times 3.4 to the power 2 because x is 2, and here is the position of 2 factorial. So you know that this value is going to be 1, and e to the power negative 3 by 4 is common to each term, so you can take this common out from all these terms. So it is e to the power negative 3.4 inside the bracket. Here you left with 1 plus 3.4 by 1 factorial plus 3.4 square over 2 factorial. So this term I have added in order to let you understand that how we apply the Poisson formula to this situation. But once you become used to of that, you don't need to write this step. Just you know that this sort of thing is going to be 1 over here. If you take out e to the power negative 4, it's going to be 1 plus lambda by 1 factorial. It will be like this: e to the power negative lambda 1 plus lambda by 1 factorial, then lambda square by 2 factorial. If there is another term, then there will be like lambda 14 by 14 factorial. So you can see the pattern how it is going on here, and then you can write it directly instead of writing all this sort of thing in detail. And now again, this is the turn to use calculator. So in the calculator, I'll first work for the calculation inside the bracket. So it's going to be 1 plus 3.4 divided by 1 factorial. I don't write it because this is going to be 1. So plus now 3.4 square, and then divided by, and I also know that 2 factorial means 2, so I'll divide this by simply 2, and my answer is e to the power negative 3.4 times 10.18. And when you multiply this with e to the power negative 3.5, so it is 10.18 times shift ln, I'll write bracket, so this is minus 3.4, then close the bracket, and now my answer is 0.3397398 and something like that. There are a few more decimal numbers, and then if you round this off to 3 significant figure, you have to check with all these sort of things. So it is 0.3. now its neighborhood is 9, so this is 3, its neighborhood is 7, it's more than 5, that means it's going to be 10, and 10 then 4, so it will be 4 0 up to 3 significant figure. Okay, now we have 2 more sums in this example that in question number 3 we have done. Now we shall see here question number 4. It says that px is bigger than 4. So in question number 4 we calculate px is greater than 4. So px is greater than 4. There is again problem with that. So bigger than 4 numbers are 4, 5, 6, 7, 8, 9 and so on. I don't know. We may not know how long it will go ahead. Therefore, this is good idea to apply the complementary theorem of probability. So here I will write 1 minus p x is less or equals to 4. At this moment, you don't need to write everything from 0 to 4 here, because in order to save your time, you have already calculated up to x less than 3. That means you have calculated up to 0, 1, 2, 3. So what you can write here inside px is less than 3, then we put the same value here and plus. So here we have already worked for the value up to 2 because it is less than 3. Now we start with 3. So px equals to 3. So we work for only 3 and px equals to 4. Now it is 1 minus, this value is already calculated in question 3. So it is 0.340 and plus, you know that every time e to the power negative lambda value is it is 3.4 is common out, and then inside it is x equal to 3. So we have lambda q, that means 3.4 to the power 3 over 3 factorial, and similarly here 3.4 to the power 4, and then in the denominator there is 4 factorial. Now we take the calculator and then we calculate these values, and by using the calculator I can see this value as like this. So first of all I'll work with this bracket. So it is 3.4 to the power 3 and then divide by 3 factorial, means you can see here it is shift and then factorial is in the bottom of this key. So this is 3 factorial, then plus 3.4 to the power 4 and then divided by 4 factorial. So 4 then shift 4 factorial, and our answer is here. Now I'll further go with this. So multiply by e to the power negative 3.4. So shift ln bracket negative sign 3.4, close the bracket, and then our answer is this. So and finally if you add this 0.340, so you write here plus 0.340, then our value is, it is 1, and minus our value is 0.7 4, 4, 4, again 4, 1, 7, and something like that. And then we deduct this value from 1, so minus 1. Our answer will be in negative sense, but we have to write in positive sense here. It is 0.255, again 5, 8, 2, and something like that. And now you need to round it off to 3 significant figure. In that case, it is 2, 5, and 6 up to 3 significant figure. And this is your answer. Now we have one more problem to solve. So that is given as x is between 1 and probability of x is between 1 and 3, where 3 is included. So here as 3 is included, so let's first of all write it. So it is p 1 less than x less or equals to 3, and it means it is p x must be bigger than 1, where 1 is not included, so you start with 2, so p x equals to 2, and then it will go up till 3, so p x equals to 3. So this sort of inequality says that x is one value of x is 2 and another value of x is 3, because here 1 is not included according to this sign of inequality, but here according to this sign of inequality and also equal, it includes 3 as well. Therefore we have this situation. Now when you apply the same formula of Poisson distribution like in here, so we know that this sort of thing is going to be common out, so we write it directly here, e to the power negative 3.4, and then I start the bracket, and then x equals to 2 means we have to write 3.4 square over 2 factorial plus 3.4q over 3 factorial, and then close the bracket, and by using the calculator my answer is 0.412 if I round off this to the 3 significant figure. So in this way we can apply the Poisson formula to the problem